gonna continue with the next contribution right now from the Fraunhofer Research Institution for Casting, Composite and Process Technology from Augsburg, as well as Augsburg University of Applied Sciences and Institute for Machine Tools and Industrial Management from Technical University of Munich from Germany. The authors are Mr. Schreiber, Klöber-Koch, Bömelburg-Zacharias, Braunreuther and Reinhart. The contribution is entitled Automated Quality Assurance as an Intelligent Cloud Service Using Machine Learning. We are looking forward to your video presentation.
Hello everyone. The topic that I'm going to talk about today is automated quality assurance as an intelligent cloud service using machine learning. My name is Johanna Bömelburg-Zacharias. I'm from the Fraunhofer Research Institution for Casting, Composite and Processing Technology, and I've been working on this paper with my colleagues Martin Schreiber, Jan Klöber-Koch, Professor Stefan Braunreuther, and Professor Gunther Reinhart. So why would you need automated quality assurance? The objective is to ensure competitiveness of manufacturing in Germany. And how would you ensure that competitiveness? This is by manufacturing products of the highest quality possible and also in highly automated production systems. The challenges that we're facing are increasingly shorter product life cycles, and therefore production lines have to be adapted and redesigned at shorter intervals. And this poses additional challenges for quality management. The use case that we're looking at in this paper is visual inspection. How does that work? This is basically just a worker looking at samples of manufactured products at the end of the production line, and this is done by hand. So this is pretty monotonous work. It's very difficult to reproduce and standardize because it's done by hand, and there's a natural performance fluctuation over the course of the day, and it's also pretty expensive. So by automizing this process, this is fatigue-free, reproducible, and economical. Now on to the intelligent cloud service part. Why would that be required? The reason for that is that we have more and more data availability. It's increasing continuously, but at the same time, we also have a lot of companies that do not have the know-how to use the available data and to gain knowledge from it. And a smart service platform can solve this problem by enabling collaboration and knowledge sharing between operants and service providers. So the operator would use the smart service to analyze the available data, and thereby the smart service helps increase productivity. And these smart services, they're provided via online platforms and allow the providers and the users of intelligent data collection and analysis to link. So let's talk about the state-of-the-art in image processing. The objective is to automatically evaluate images by software. The traditional image processing chain is made up of 5 parts. The first step is image capturing, where you just take a picture with a camera. The second step is image preprocessing, which is used to improve the image data by correcting for distortions or enhancing image contrast. The third step is segmentation. In computer vision, image segmentation is the process of partitioning a digital image into multiple segments. So that will be sets of pixels. And the goal of segmentation is to simplify the representation of an image into something that is more meaningful to analyze. Step number 4 is feature extraction, which reduces the number of resources required to describe a large set of data. You use an algorithm to detect the desired shapes or features within the digitized images. The last step is classification, where you recognize the different categories of image types that you fed the algorithm. We combine the traditional image processing chain with machine learning. which is a branch, machine learning is a branch of artificial intelligence where knowledge is generated from experience through algorithms. And this simplifies the image processing chain by quite a bit because it just incorporates a lot of the steps automatically. Artificial neural networks and deep learning simplify the image processing chain. They extract the necessary information directly from the original image without intervention from a developer. So this is a huge plus that you get with machine learning. Now on to our approach for automated quality assurance using machine learning. The first part to consider is the smart service component. And a single service is self-contained and can be used independently. That's our baseline assumption. And this service is supposed to be available via an interface within a network in the end. Then onto our selection of machine learning algorithms and parameters. So what we have chosen for image processing is a convolutional neural network, a CNN, which is a special type of artificial neural network with a grid-like architecture that uses convolutions instead of a matrix multiplication in at least one layer. The pooling function in a CNN replaces the CNN output with a statistic summarizing the nearby outputs. And that is how the pooling function contributes to making the model approximately invariant to small changes in input data. The output therefore does not change with small shifts in the input data. And we have chosen CNNs basically because they're very successful in they're very successfully used in image classification. And another technique that we have been applying is data augmentation, where you can scale and crop and rotate and flip the images. So you basically just get more data for training later on. The industrial case study that we've been looking at is a production line for injection molded parts of a household appliances manufacturer. The components that it's made up of are an injection molding machine, a removal unit, a transport robot, 2 delivery belts with manual quality inspection stations, and the manufactured products themselves. So that would be transparent plastic parts for household appliances. These plastic parts are visible components. They are a direct interface to the customer, and therefore we have very high surface quality requirements. There must be no foreign particles. And the current situation is manual inspection by a worker at the end of the production line that decides whether the parts are okay or not okay. And I have a video here of the test bench that we have. What you can see in the video is the robot picking up the injection molded part and placing it on a mount for the part. And then the robot takes several pictures of the part with a camera. And we chose a monitor for lighting, and we also experimented with different background patterns on the monitor to increase the contrast. And one example that you can see are the black and white stripes. So those can be seen on the monitor in the background. And after the robot is done taking the pictures, it removes the part from the mount and places it onto the next delivery belt. We're also continuously improving and developing the test bench. And so we implemented a second robot to improve flexibility of the setup. And that's what you can see in both of the pictures. Our main goal in the end is that we want to teach the computer to recognize images and classify them into different defect categories. And what you can see on the right-hand side is the part that's to be inspected. And then you can see different defect categories like air inclusions, cracks, or a scratch. And these defects, they happen due to the process. So you have fluctuations in the quality of the injection molded parts, and rejects occur. The possible defects that can happen are air inclusions, cracks, scratches in the surface, and run marks from injection molding. And since we have those high quality requirements from our customers, faulty parts must not get into the final assembly, and we need a 100% inspection of the parts. The way that we trained and tested our service that we developed for automated quality assurance is by using a semi-factorial experimental plan. And the objective of that experimental plan was to determine the parameters of the CNN, the convolutional neural network that achieves the highest possible classification accuracy for the test dataset. And our main assumption was that classification accuracy of a neural network can be influenced in two basic ways. So the first one is data. So there could be the amount of data, so that will be the size of training data set, the quality of the data. So one factor here would be image resolution, and also using data augmentation to create more data. And the second way that we thought that classification accuracy can be influenced are the training specifications. And there you would look at the percentage ratio between the training data set, the training data set, and the test data set, and the number of training iterations. So that's how we set up our semi-factorial experimental plan. There's two different ways to classify the parts. The first one is simply binary, so that would be an okay or not okay classification. But what we really wanted was a defect-specific classification where you can identify scratches or run marks or error inclusions, etc. And the procedure for the application was that we took the labeled training data, then we trained our neural network, and we tested it, and thereby we predicted the part quality of it, or the defect class. And then we could apply the neural network in the end by just taking the input data from the production line and predicting part quality. Here's another look at our semi-factorial experimental plan and the 7 factors that we identified that can be varied to achieve better classification results. Number 1 is the batch size. Number 2 is the dropout rate. Number 3 is the split ratio of training and test data set. Number 4 was training epochs, and number 5 is data augmentation. Number 6 is image resolution, and number 7 is the size of the data set. And the classification results are presented within the publication. Here's an excerpt of our results. So on the left-hand side, you can see what happens with data augmentation and how our accuracy increases over multiple training epochs. And on the right-hand side, you can see what happens without data augmentation. So you can see that without data augmentation, there's an over-adjustment to the training data set, but there's no improvement of the classification accuracy for the test data set. So that's something that we want to avoid, and why we use data augmentation. Our resulting best parameters, where we reached a classification accuracy of 86.25%, have been, they can be seen in this table. So the batch size has been 16, and our training test data set split was 80-20. We did not use any dropout rate because that did not improve results. our training epochs that have been necessary were 50, and we did use data augmentation and an image resolution of 150 by 150 pixels. So to summarize our paper, the initial situation that we started with was a manual inspection of the injection molded parts. You can see the injection molded part in the right picture. And the objective was to automize that visual control and incorporate a service aspect. And the approach that we took was to train a machine learning algorithm, namely a convolutional neural network, to classify those injection molded parts. And there has also been a service concept incorporated. And the results that we got were a classification accuracy of 86.25% in quality assurance. And we identified the best parameters with a semi-factorial design plane. And in future work, the classified defects can be combined in an analysis with the process parameters from the injection molding process to improve and stabilize component quality. Thank you very much for your attention.
Thank you very much for your presentation. For those of you who has just turned in, we are on live stream 2 of the Global CIRPe Web Conference 2019 on day 2. We have been just listening to the presentation of our colleagues Martin Schreiber and Johanna Bömelburg-Zacharias. We are going to have a question and answer session with them regarding your questions on the live chat right now. So can you hear us?
Yes, we can hear you.
Martin, can you hear us too?
Yes.
Great. Okay. So we have 2 of our authors of this contribution online at the moment. Maybe some of you could already see on the YouTube live chat one question from Yamila Omar. Thank you for your question, Yamila. I'm just reading it for all of you. Quality is a tough call for ML because of the number of the faulty parts is very low compared to the number of parts that are up to the standards. How big is your data set and how many classes of defects are there?
Okay, I'm going to answer the question. So we had around 50 parts, and we used data augmentation to increase the data set. And then we had 4 different defect categories and around 10 samples. And so we took 6 images of each part. And so we had numerous images of the same defect from a different perspective, and that's how we increased our data set. And then we also used data augmentation, so we put the images and we rotated them. And that, yeah, that's what we did.
Thank you for your
from my perspective, sorry, just wanted to add, like,
sure.
Like in general, that's true. Like you need quite sufficient data set for machine learning to work, like in general. But from our perspective, like in comparison to predictive maintenance, etc., like the producing of quality parts or the quality inspection, rather, or is like providing more data than a lot of, or at least what we found in this research project. So it worked in general quite well, and for us that was the reason how to tackle that problem.
Thank you for your answer. I'm going to ask Yamila Omar to comment on YouTube if the answer is remaining for him or if there are other aspects he would like to ask you further. I'm continuing with the second question of Ahmet Yükseltürk, who has also pushed a question on live chat, and he's asking for how do you classify the parts that have more than one defect?
So we didn't really have one that had multiple in the same spot, so we would see it only in part of it, and then we would classify what the defect that was to be seen, and so we didn't have that result basically with several defects in the exact same image. So.
Okay.
We just classified the images because we knew what the defect was in the part. Yeah.
Okay, I also would like to recommend your answer to Ahmed if the answer is sufficient or not. And I have another question regarding your acknowledgement. You have acknowledged a project funded by the German Federal Ministry for Economic Affairs and Energy, Open CIRPe, and which is also managed by the German Aerospace Center. Could you just give an insight about the whole idea of the project and how your paper is related within the project, as well as for the production engineering community of CIRP?
Yes, of course, I will answer that one. OpenCIRPe is a research project which started in the beginning of 2016 and was finished in the beginning of this year, in the middle of this year. And the general objective of this research project was to develop smart services in different kind of aspects. The one that we have seen here, quality inspection. We have also tried to develop a predictive maintenance smart service, a predictive quality service, and there is this research still is going on. So we have achieved quite a good achievements, but as I already mentioned in my previous answer, within predictive maintenance it's a little bit more challenging in general, so that's why we need to continue this research.
Thank you very much. Both of the commenters have already thanked to you on live chat. Maybe you can see it. So I would like to thank you for your time and hope to see you soon. Thank you, both of you. Bye.
Bye.